Last lecture was over polynomial functions that were of degree 2. So those were quadratics. What do graphs of quadratics look like? Did we do last night's homework? What do parabolas? Very good. So they're the U-shaped things, right? Okay, so quadratic function we know how to recognize now as squared, and these look like U's. This is a polynomial, and we say it's a polynomial of degree 2. Linear functions look like straight lines, and these are polynomials of what degree? Degree is the exponent, degree 1. Then we have constant functions, and these are constant, so they're equal to a single number. And these are degree what? Yeah, these are degree 0. Okay, and because there's no variable, we say it's degree 0. So we're saying what's the highest exponent, okay, of your variable? Here we have no variable. Okay, but we're familiar with these already. We now want to graph polynomials of higher degree. Okay, and how high do we go? Probably, practically speaking, as high as degree 6 polynomials. But this is how we write a general form polynomial. Specifically, an minus 1, a2, a1, and a0 are all just constants. They're all numbers. But what's your favorite number? 3, 5, 7. You guys don't have any weird favorite numbers? What about no favorite decimals? 3.21? Pi? Okay. Only whole numbers? Okay. Anyway, 3x to the 5th plus 5x to the 4th plus 7x squared. Maybe I'll include a negative. Negative 3.21x plus pi. This is an example of a polynomial of what degree? So highest power, we'd say degree 5. The rule we should memorize here is these constants out in front should be real numbers. Let's say the coefficients, an all the way down to a0, are real numbers. Okay, so when would we not have a polynomial? So first, we want to recognize polynomials 4x to the 5th minus 3x to the 4th plus 2x squared, because these are all real numbers in front, and the exponents are all just positive integers. The exponents are positive integers or whole numbers. Okay, so how do I recognize something that's not a polynomial? A square root of x is an exponent of 1/2, x to 1/2 power. So that's not an integer exponent. If I divide by x, that's really x to the negative first power. So it's not a positive integer exponent. And here, my problem is 3 plus 2i is my coefficient, and it's not a real number. Any questions about this? So in math, we love polynomials because you can create polynomials that can approximate any curve. In one of the upper division math classes, we would take a silhouette of someone. Does that look like someone? Right? And we'd say, it needs to be a function, so it has to pass the vertical line test. This does not pass the vertical line test, right? So I need to break it up into pieces. Doesn't look like anyone you know? All right, I'd go from here to here and say I could create a polynomial that looks like this. And I could graph that portion, and I could create another polynomial that goes from here to here and looks like this. So we can create cool looking images using polynomials to arbitrary accuracy. And you go all the way around. This is one of many reasons why we like polynomials. Okay, but what are they? If we graph them, they are smooth continuous curves. So they look like this. I can draw it without picking up my pen. And they're smooth, meaning there's no abrupt changes in direction. There's no corners. So this absolute value graph has a corner, so it's not smooth. Or we might have something like this, which we call a cusp, but it's also not smooth. Then we have something that I can draw, but only by picking up my pen. There's no way to connect those two lines without picking up my pen. So that's not a polynomial. And finally, what's this type of graph called? If I have a different function here, yeah, very good. It's a piecewise function. I have to pick up my pen to draw it, so it's not a polynomial. Any questions about that? One thing that all polynomials have and have a distinct pattern of is what we call end behavior. End behavior means if I look far enough to the right, what happens? If I look far enough to the left, what happens? Yes. They go off to infinity. Always. For instance, let's look at 4x to the fifth minus 3x to the fourth plus 2x squared. If I go very far to the right, what values of x am I talking about? Positive infinity, but infinity is not a number, so I like to plug in a very large number. 100. Okay. What's 100 to the fifth? What's 100 to the fifth? I do. It has two zeros. That's one exponent. Then another two zeros would be a second exponent, a third exponent, a fourth exponent, and a fifth exponent. What is this number? 10 billion? Okay, times 4. What about the x to the fourth? How does it differ from this number? It'd have two less zeros. How many would that be? 1, 2. Oh yeah, 8. Thank you. So this number is 100 times smaller, right? What if I plugged in instead of 100? What if I plugged in 1,000? This one would be how much bigger than that one? 1,000 times bigger. What if I plugged in 1,000,000? 1,000,000,000,000. I'm going as far right as you can think of, right? This is so much bigger than x to the fourth for large numbers that we can ignore it. Okay, so our end behavior says we ignore these other terms and only care about the highest power because it's so much bigger. All right, so it turns out these ones that have even power for their lead term are very much the same. If I go to the left, I go up, and if I go to the right, I go up. Why is that? We have a very large number. If I plug in negative 100, it's always positive still, right? To even power. If it's odd, it's opposite. If it's odd, I plug in a large number. To the right, I go up. But a negative large number would be negative. So it goes down. Okay, so here's some math notation that shows up on your homework. As x goes to infinity, we're going which direction? Left, up, down. Very good. This is right. X goes to infinity is to the right. As x goes to negative infinity, we're going into what direction? Very good. Left. X goes to negative infinity. F of x goes to infinity, we're going what direction? Very good. And f of x goes to negative infinity, we're going what direction? Down. That's your y value. Y is going up or down. Okay, turns out we only have 4 scenarios for the end behavior. If your exponent is even and your coefficient, and your coefficient is positive, then they're both going to go up on both sides. If it's even and the coefficient is negative, then they both go down. If the leading coefficient is odd, this typo is awful, I'm sorry, and the coefficient is positive, then it goes right and up, left and down. If the leading exponent is odd and this term is negative, the lead term is negative, And it goes left and up, right and down. Okay, let's try and apply this example. P of x equals x cubed minus x. I care about which term? X cubed. I don't care about the small exponent term. X cubed, I would say that lead number, a is equal to 1, which is positive, and my exponent is odd. In which case, I'm talking about this behavior. But I like to double check because my memory is awful. The way I double check this is I plug in my favorite large number. What's your favorite large number? All right, 2000. I'm going to do 1000. When I plug in 1000, I'm really saying as x goes what direction? To the right. I'm really saying right. As x goes to infinity. Okay, and then if I cube it, I'm really saying my y value goes which direction? Yeah, so 1000 cubed is positive. It's positive, which does mean it's going up. We say P of x goes up to positive infinity. Any questions about this? Let's plug in our favorite number to the left. I'm going to go with negative 1000 since we plugged in 1000. So I'm really saying as I go to the left, as x goes to negative infinity, what happens to my y value? Negative number cubed would be negative or positive? Negative, which means down. So we say P of x goes to negative infinity. Any questions about that? I'm going to skip to part D. Okay, I care about which term and the sign in front, right? So I only care about the lead term, negative x to the fourth. Okay, so what is my lead coefficient? Negative 1. So it's negative. And my exponent is even. So even exponents, we know they either both go up or both go down. The term is negative. We know they both go down. This is this scenario, but we don't have it memorized. We just plug in our favorite large number, favorite negative large number. Negative x to the fourth. Plug in 1000, meaning as I go to the right, what does it spit out? Negative or positive number? Positive, but then we apply the negative at the end, so it spits out a negative. To the right means as x goes to infinity, my y value is u of x goes to negative infinity. So I go right and we plug in to our lead term, our favorite negative number, negative 1000. So as I go to the left, does my y value go up or down? So negative number to an even power is positive. Then I apply the negative. So yeah, it goes down. So we say that as x goes to negative infinity, my y value, u of x, goes to negative infinity. Any questions about end behavior? Yes. For instance here, odd exponents always go in opposite directions because a positive number to an odd power is positive. A negative number to an odd power is negative. But when you multiply by the negative, it's going to flip it to negative and flip this to positive. Yes. So we can name the function whatever we like. Why don't I just write y is equal to 9 plus 8x squared minus x to the fourth? Do we just want to confuse you? Why would I use u of x? This is a function notation, and it allows me to specify which x value I'm plugging in. So that's one advantage of function notation. The other advantage is I can name it. I can call it u, or I could call it even sine. This is another function where the name is sine. So this function notation allows me to name it and be more descriptive. Also, it allows me to specify what x value am I plugging in. Real zeros of a polynomial function. This is something that was on the test. Zeros of a function means what? Yeah, the x-intercepts. So when is your function equal 0? Which one do you want to solve? This one or this one? Or left or right? Okay, I heard left. When is p of x equal to 0 for which x values? On your test? Yeah, very good. Make one side 0 and factor. We always factor out the lead negative. We take out a negative x, and we have an x squared minus 8x plus 16 equals 0. Factors of 16 that add to make negative 8, negative 4, and negative 4. So our solutions are negative x equals 0, or x minus 4 equals 0, or x minus 4 equals 0. X equals 0, or x equals 4. That's just a review of what we've done in the past. We can find zeros by factoring. Does factoring always work? No. And that's the whole point of chapter 3. How do we find zeros when factoring doesn't work? And the answer is it's really complicated. We're going to do a whole systematic way of guessing and checking. But before we do that, we're going to use logic to determine if there's zeros. And the logical tool we're going to use is called the intermediate value theorem. What does intermediate mean in the dictionary? Somewhere in between, something like that. Okay, so I'm going to read the theorem and then we'll draw a picture representing what this means. Consider a polynomial. We'll name it p of x. P for polynomial. In an interval a, b. So these are our x values. Let me start graphing. Here's a, an x value. Here's b, a different x value on the x-axis. P of a is not equal to p of b. What does that mean? P of a is not equal to p of b. What does p of a represent on my graph? It's the y value when x is what? A. So when x is a, let's say this is my point. A, p of a. That means that my height is p of a. So what does it mean that p of a is not equal to p of b? The y values are not equal. So if I go down here, I know my point's not here. It's any other height. I'm going to pick a height over here. B, p of b. Okay, if the y values are not equal, what the intermediate value theorem says is I have to hit every value between p of a and p of b. So what do we know about the graphs of polynomial functions? We have two words to describe them. Look back in the notes. Smooth and continuous. So that means I can't draw something like this with corners, right? And continuous means I can't pick up my pen. Does that make sense? So can you imagine every possible way I can connect these two dots? Yeah? Any way I connect them, I have to hit every value in between p of a and p of b. Because I can't pick up my pen. Okay, so p of a cannot equal p of b. So let's heights aren't the same. Well, I hit every y value in between. The only way this would be possible to skip a y value would be to have a discontinuous graph, not a polynomial. And this one skips the y values between here and here. Okay, so how can I describe this in words? P will hit every height or y value between P of A and P of B. How can I use this theorem to prove there's a zero? I have a polynomial here. Can I factor this? I guess this one is factorable, huh? Okay. That's not too helpful. Wait, is it? No, it's not. I'm sorry. This is a cubic. We actually don't know how to factor this at this point. Okay. But we're going to use an intermediate value theorem to prove there's a zero because we can't factor it. Okay. The first thing we're going to do is we're going to look at the values x equals 1, x equals 2. Here's 1. Here's 2. I need to find the corresponding y values. What's P of 1 equal to? Very good. -2. So I could plot this point 1, -2 here. Then I want to find the point P of 2. What do I get? So 2 cubed is 8 minus 4. We get 4. Okay, so the intermediate value theorem says my polynomial must hit every y value between -2 and 4. So why does that mean I have a 0? Y equals 0 is between -2 and 4. Right, 0 is between these two. That means somewhere in the middle, I don't know what my graph looks like, but it's got to cross this axis at least once. How do we write this up in formal words? Since P of 1 is negative and P of 2 is positive, by the intermediate value theorem, are you okay with me writing IVT for intermediate value theorem? By the intermediate value theorem, P of x assumes every y value between -2 and 4. Since 0 is between -2 and 4, P has a 0 for some x in the interval 1 to 2. So you'll want to answer this question in a similar manner. You do not have to draw the graph, but you want to quote the intermediate value theorem and explain why it's going to hit 0. Now we get to the meat of the section. The following are equivalent. X minus c is a factor of the polynomial, means x equals c is a real solution. The P of x equals 0. X equals c is a real zero of the polynomial, and c comma 0 is an x-intercept of the graph. You want to memorize this, but more so in terms of an example. You want to have an example in mind. Example 4 will be the first example. So I have a graph here. What are my intercepts? Actually, what are my x-intercepts? -2, 0, 1, 0, 3, 0. So this is the fourth example here. These are my intercepts. So what are my c values? C1 is equal to -2, C2 is equal to 1, and C3 is equal to 3. Okay, so these are my zeros. X equals -2, 1, and 3. Now we're going to apply the first rule to factor the polynomial. Based on the graph, I found my zeros. And every polynomial can be written as your lead term times all of your linear factors multiplied together. So in terms of our specific polynomial, our a value is what? The leading number is 1. So we can put that 1 out in front. Then I have x minus, what's my C1 value? Yeah, -2. What's my C2 value? 1. And my C3 value? All we had to do was look at the intercepts and subtract those values from x to get our factored form of our polynomial. X plus 2 times x minus 1 times x minus 3. I factored the polynomial by looking at the graph and using this theorem. Any questions about that? The next theorem, even and odd powers of x minus c. So this corresponds to a factor. And we know that those factors correspond to zeros. So one thing we'd really like to know is when will our graph go through the zero, pass through it, and when will it only touch and turn around? It turns out it has to do with the exponents. So for instance, y equals x squared looks like this. It has a 0 here at 0, 0, and it doesn't pass through it. It touches and turns around because the exponent is even. So if your exponent of your factor is even, it doesn't pass through the 0. Another example would be y equals x cubed. It has a 0, really x minus 0 cubed, and the exponent is odd. When the exponent's odd, your graph will pass through the 0 to the other side of the x-axis. Okay, so we're talking about the exponents being odd or the exponents being even. Example 5 is asking us to use this theorem to come up with a cubic polynomial that represents the graph given. Okay, so any polynomial can be written as the lead term times its zeros, but now to different powers. First off, how many zeros do I have? To x equals -2 and x equals, maybe I'll say C1 is equal to -2. C2 is equal to 1. So I'd like to subtract -2 and I'd like to subtract 1. Can anyone tell me what's the exponent of x plus 2? We'll just say even or odd. It passes through, so I know it will be odd exponent. Okay, so I'm going to have an odd number here. And what about for x minus 1? It touches and turns around, doesn't pass through to the other side. So we say that x minus 1 has an even exponent. But what's the smallest even number? 2. Smallest this could be is 2. And the smallest odd one would be 1. Now, I could have plugged in 4 and 3 and would have had the same behavior through my zeros. Why did I pick 1 and 2 instead of 4 and 3? The exponents must add to make 3 because it's a cubic. But any odd number would do and any even number would do. I wanted one to add to make 3. Exponents must add to make, because it's a cubic. The last step, I have to find that leading coefficient of A. So we're going to use this third point on the graph, 0, 1, for my x and y value. 1 is equal to A times, 0 plus 2 to the first power times 0 minus 1 squared. That will give me 1 is equal to A times 2 times -1 squared, which is just 1. So if I solve for A, what do I get? Okay, I'll do one more step. 1 is equal to 2A. So I'll divide by 2, and I get 1/2. My function y is equal to 1/2 times x plus 2 times x minus 1 squared is my polynomial of degree 3. This has what 0? Example 6. If I set this equal to 0, x equals 4 would be a 0. And yeah, very good. X equals -3. For x equals 4, does my graph pass through at the 0, or does it touch and turn around? Yes. P of x passes through the x-axis because exponent 3 is odd. What about x equals -3? My graph of P of x, we say it has x plus 3 has an even exponent. So the graph intersects, but does not cross the x-axis. This is because the exponent of 2 is even. This brings us to graphing. Which one do we want to do? I'm going to skip to example 8. First, what is the end behavior? So we're integrating everything at once here. End behavior. If I FOILed this all out, I'd have an x times an x squared and the negative 0.1 out in front. So my lead term, negative 0.1 x to the 4th. So I would go left and up or down? Down. Why down? Down is correct. So you plug in your favorite negative number for x. We're definitely not gonna have time to do all this. Okay, so this homework assignment, do as much as you can. I'm going to send the due date. So I want to make sure we master it. We'll slow down a little bit. I do want to start graphing this. So make sure you master that portion and understand why this is going left and down, right and down. So it occurs to me I did not define multiplicity for you. So the multiplicity of a 0 is the number of times it occurs, which is the exponent of the factor. So if x equals c is our 0, x minus c raised to the power of m would be our multiplicity. So going down here to example 8, what are the zeros? X equals 1 has multiplicity what? Yes, because the exponent here is a 1. So that's multiplicity 1. The next one is x equals -2 has multiplicity what? 1 because it's exponent. And the last one, x equals 4 has multiplicity what? 2 because of this exponent. These zeros correspond to intercepts, x-intercepts. If the multiplicity is odd, what do we know about the graph and the intercept? How does it interact? Does it pass through or does it just touch and turn around? Yeah. If it's odd, it passes through. Yeah. Yes. Okay. If the multiplicity is even, yeah, it just touches and doesn't pass through to the other side. Okay. So just to talk about from last time, I want to make sure you read through the notes and understand every definition. What's the degree of a polynomial? The degree of the highest exponent would be the degree of the polynomial. What do you know about the graphs of polynomials? You should memorize that they're smooth and continuous. What are examples that are not smooth, not continuous? Did you all memorize the end behavior? Not yet? Okay. Make sure we memorize the end behavior. Do we memorize the intermediate value theorem? And this is the important one. They're all important. But if x equals c is a 0, then x minus c is a factor. And c0 is an intercept. Even power or even multiplicity, when we touch the 0, we don't pass through, we turn around. If it's odd multiplicity, we do pass through. So you want to read through those, make sure you understand every theorem, and then can apply it to the homework. And ask questions if there's something you don't understand. Let's practice graphing. So by Monday, I expect us all to be able to graph all polynomials that exist? Okay. If you did the homework already, I recommend trying example 7 and 8 on your own right now. What is the far left behavior of q of x? Oh. This is polynomial q of x, negative x cubed plus 4x. Okay, so let's say to the left, or as x goes to negative infinity, what happens to my graph? Okay, so it's dependent on the lead term, right? The lead term is negative x cubed. So you either memorize odd means opposite directions, okay? But the negative in front affects which way? I like to check with a far left number. What's a far left number? What? Yes, far left numbers are negative on my x-axis. Wow. -1 will technically work, but far left would be like -1,000,000, right? -1,000. So the point is, if I plug in that, this is saying as x goes to negative infinity, is my answer negative or positive? Negative cubed is negative times a negative is positive. So that means we go up. So left and up is the conclusion. Q of x goes to positive infinity. So I know my end behavior will be left and up, right? And yeah, it's always opposite for odd exponents, but should we check? So as x goes to positive infinity, the right here, negative, now I'm plugging in positive 1,000, x goes to positive infinity. What's my answer? I get a negative number. So that means I go down. Down. Q of x goes to negative infinity. Are we comfortable with that? Okay, here's another way that would be even shorter. Think of the easiest odd exponent function. What's the easiest odd exponent function you think of? Y equals x to the power of 1? Okay. X to the power of 1, but keep the sign negative in front. What does that graph look like? It looks like this. So to left and up, so right and down. You can just do the analogy where this is a negative coefficient odd exponent. The easiest one with a negative coefficient and odd exponent would be negative x. So my graph will have the same end behavior as negative x. All right, now that I've killed that subject, how do we find the y-intercept? Yes, plug in 0 for x. How many y-intercepts do I have? How many y-intercepts do I have? Is this a difficult conceptual question? Polynomials are functions, which means they pass the vertical line test, which means they can only have one y-intercept. What would mean to have multiple y-intercepts? It would fail the vertical line test. There's one y-intercept. What is q of 0? 0 cubed plus 4 times 0 is 0. 0, 0 is on our graph. How do we find the x-intercepts? Plug in y is equal to 0. When is q of x equal to 0? Negative x cubed plus 4x is equal to 0. We solve by factoring. If I take out negative x, I end up with an x squared minus 4. Can I factor it further? Difference of squares, yes. Difference of squares factors into x minus 2 times x plus 2. But when is negative x equals 0? And x is 0. So this is 0, 0. When is x minus 2 equal to 0? 2. Okay, so 2, 0. And when's x plus 2 equal to 0? Negative 2, 0. What's the multiplicity of x equals 0? This has exponent 1, so it has multiplicity 1. but more important, odd multiplicity. But what about what's the multiplicity of x equals 2? More importantly, it has odd multiplicity. And what about x equals -2? Also 1. So I already have enough to graph the general shape of this function. Let me try to make some tally marks that are evenly spaced. I don't know if you struggle like I do making these evenly spaced marks. How's that look? Let's plot the points. 0, 0. What else? 2, 0. Oh, 2, 0. -2, 0. Why does that happen? Why do they disappear? Okay, so I have end behavior, left and up, right and down. I draw a smooth continuous graph. When I hit this point, do I touch and turn around or do I pass through? Why do I pass through? Odd multiplicity. Then at some point, what happened? At some point, I turn around and I have to hit this other 0. Do I turn around or do I pass through? Because odd multiplicity, and I have to go here. Pass through because odd multiplicity. My graph looks like this, or maybe it looks like this. All I know is the end behavior and my zeros. So how can I be more precise? Plug in some points, some in-between points that are missing. Step 4, oh no. Draw. Step 4, we need to pick up or plug in some intelligent points. Plug in x value. Which x values do we have? -2, 0, and 2. I'd like to plug in things like 1, -1, and how about 3 and -3? Okay. If I plug in 1, what do I get? Where is my function? What is -1 cubed plus 4 times 1? 3. Okay, 1, 3. I'm not going to plug in the red ones. I know they're 0. We already found those. So let's plug in the green ones. What if I plug in -1? Wait a second. No, not -5. Wait a second. Let's use the fact that this has symmetry to graph it more quickly. So from our tests, how can we tell if this is even or odd? Plug in -x. What do we get? -x cubed plus 4 times -x. -x cubed is -x cubed. Yeah, okay. But what about, and then the double negative cancels to make a positive x cubed. Is it odd? So is this equal to, should say, is q of -x equal to -q of x? Negative times negative x cubed plus 4 x. If I distribute the negative, I get positive x cubed minus 4x. Hey, these are the same. Which tells me what? It's odd and symmetric about the origin. So that means if I draw the right half, I know what the left half will look like. So if I plug in 3, I get -3 cubed is -27, plus 4 times 3 is plus 12 is -15. What do I know about odd functions? They're symmetric about the origin. So that means the other one will be symmetric. So if I flip the x value, 1, 3, I flip both the x and y value, becomes -1 and -3. I can plug in to double check. If I have 3, -15, I flip the x and I flip the y to get -3, +15. So we know the rest of the graph looks like this. The green graph, not the blue ones. Any questions about this? Here's a question. Is this? I think yes, possibly. It looks like it, right? Turns out we cannot be sure. If you want to be sure, take calculus to find those local maximums. But that it looks like the local max, it might not be. I'm not that precise yet on my graph. If we want to be very precise, we need to find where the slope is 0. The tangent line is horizontal. Okay, any questions about this graph? Let's try another one. Let me erase all of this mess. Okay. If I expanded that, if I filled it all out, can anyone tell me what my lead term would be? Well, very close. Yes, to the 4th. If we fill this out, we'd have an x times an x squared. Negative 0.1 x times x squared, negative 0.1 x to the 4th. If you don't believe me, FOIL it all out. Lots of fun. This is the lead term. If it's even exponent, it means they're both up or both down. If the leading coefficient is negative, it means they're both down. Okay. Left and down, right and down. If that's a little confusing to you, think about your easiest even polynomial, like x squared, but keep the sign out in front. Negative x squared is a downward parabola. But what we care about is the end behavior, left and down, right and down, is the analogy. Just as a quick double check. Okay, next up, what's the one and only y-intercept? If we plug in 0, we have g of 0 equals negative 0.1 times 0 minus 1 times 0 plus 2 times 0 minus 4 squared. Negative times negative is positive 0.1 times 2 times 16. Did I calculate that? Okay, it's 3.2. 0, 3.2. Step 3, we need to find the x-intercepts. Yeah, just the zeros. So what are they? You agree with that? That's based on, if I set this equals 0, I'd use the 0 factor property. 1, negative 2, 4. Now, maybe I'll split this up a little bit, and I should denote the multiplicity of each. Yes, so the exponent has multiplicity 1, because the exponent here is 1. X equals negative 2 has exponent of 1. And this is the important one here. Yes, 2. More importantly, odd, even. Now we know the general shape of our graph. We just don't know how high and how low it goes. So let's go ahead and plot these. 1, 2, 3, 4, 5. 6. 1, 2, 3, 4. 1, 2, 3, 4. Oh, that's negative 4, sorry. 1, 2, 3, negative 4. The zeros are negative 2, 1, 1, and 4. My y-intercept, 3.2. And my end behavior is left and down, right and down. Can we imagine what this looks like? Probably something like this. Uh-oh. I'm just going willy-nilly through here. I'm sorry. When I hit this, I should decide, do I pass through it or not? Okay, so x equals negative 2 odd. Yes, pass through. I need to hit this point. It's somehow. So there's options here. I don't know. I really don't know, but I'm guessing. I need to plug in more points to be more accurate. Then we get to this point down here. Do I pass through or touch and turn around? Okay, so x equals 1 is odd. So I pass through. I need to hit that other red dot. So at some point, I don't know how far I'm going. At some point, I'm going to turn back around and hit this dot. Do I pass through? No, this one's even. X equals 4 is even. So I need to, in a smooth manner, These have to be smooth lines. Touch it and turn back around. But I'm not sure what this graph looks like. It could be even stretched out further. Oh man, this is really, I'm really struggling here. Could be stretched out further. I'm not sure. To be more accurate, we plug in more points. Step 4, plug in points. What are the x values? What are the y values? This is function g of x. So we have -2. We plugged in 0, right? We've plugged in 0, we plugged in 1, and we plugged in 4. We'd like to plug in some values in between. So some missing values would be like, what's your favorite number between -2 and 0? Yeah, -1's probably a good one, but you can definitely go with a decimal. You have a calculator. What's your favorite number between 0 and 1? Wait, actually, let's not plug in a number. We're going to connect those two dots. Let's not plug in a number there. Your favorite number between 1 and 4? No one likes 3? Okay. Let's plug in 3 also, so it doesn't feel lonely. Plug in enough points where you think you can connect the dots in a smooth, continuous way. Okay, I'm going to give the answers because we only have so much time here. If I plug in -3, I get -19.6. Wow, that goes low really fast. If I plug in -1, I get 5. If I plug in 2, I get -1. Doesn't go very low. 3, I get -1. And 5, I get -2.8. So we want to plot these ordered pairs. I'll plot them in purple. Okay, -3, -19 is down here. So I'm not going to plot that one, right? -1, 5 is up here. 2, -1.6 is about here. 3, -1 is about here. 5, -2.8 is about here. So you can see my graphs were like all over the place. If I plotted, I really don't want to draw that low one. We'll just say this goes nearly straight down really fast. No, undo. Okay. I'm going to delete these green lines here. They're really tripping me out. Is that the highest point locally? I don't know. It needs to be smooth and continuous, and it needs to be going left only. Any questions about this? Are you prepared to graph any polynomial I give you? Okay, the trickiest thing is going to be actually this. Because in order to find those intercepts, you're going to have to factor. We don't know how to factor all polynomials yet. That's what the future lessons are about. How do you always find these when they don't necessarily factor nicely? So I gave it to you in factored form, so that's a little bit nicer.